We present a learning-based method with strong physics priors to address the challenges in high-speed non-line of sight imaging. Non-line of sight imaging aims to uncover the shape and appearance of objects beyond the direct line of sight by analyzing the propagation of light through the hidden scene. The most successful approach to non-line of sight imaging is based on the time-of-flight principle. An imaging system raster scans a Rayleigh surface with pulsed laser and captures multiply bounced indirect light reflected off the Rayleigh surface using time-resolved sensors such as single-photon avalanche diode, or SPAD. The picosecond resolution time dimension of SPAD histograms encodes rich information about the geometry and appearance of the hidden scene. Consequently, the central question in non-line of sight imaging is how to invert such measurement to reconstruct an image of the hidden scene as if being captured by a line of sight camera from behind the Rayleigh surface. The standard image formation model for non-line of sight imaging introduces several approximations for the ease of analysis. For example, it only models 3-bounce light without accounting for higher order scatterings. This simplified model forms the basis of physics-based reconstruction algorithms and, importantly, is adopted for the rendering of synthetic datasets for training deep neural networks. But to what extent does this model capture the nuances in data collected by real imaging systems, especially those optimized for acquisition speed? To answer this question, let us do a quick reality check. On the left is a measurement of digit 2 rendered by a transient rasterizer, which runs at interactive rate and thus enables large-scale data simulation. On the right is a measurement of a similar scene captured by real hardware. Note the striking difference between the two datasets. The real sensor response is bumpy, noisy, and most notably exhibits distinctive vertical stripe pattern. So where does this pattern come from? It turns out that the stripes are the byproduct of a hardware trick known as pixel remapping, which is key to rapid data acquisition. The idea behind pixel remapping, as we illustrate on the left, is to scan a Rayleigh surface with a sparse pattern and record data using a pixel array, and later map the pixels to skipped positions between the scan lines to fill the gap. Pixel remapping reduces laser scanning time by an order of magnitude, resulting in an unprecedented imaging speed of 5 Hz at the expense of varying degrees of geometric error shown on the right. How do existing reconstruction methods behave in the presence of such error? We focus on methods for non-confocal reconstruction as pixel remapping is only implemented with non-confocal imaging hardware. Please refer to our paper for a comparison between confocal and non-confocal setups. Phasor field RSD is a physics-based method based on diffractive wave propagation. While it is fast and robust to the approximations, it is limited by sampling rate and hence yields blurry reconstruction. On the other hand of the spectrum are learning-based methods including LFE and neural transient fields. They are exclusively trained on synthetic data as it remains infeasible to collect real data at scale. While these methods behave strongly on synthetic test data, they cannot account for the large domain gap and thus fail to generalize on real captures as we demonstrate later. Further, neural transient fields require lengthy per scene optimization and cannot learn statistical priors as in feed-forward methods. LFE, on the other hand, supports feed-forward inference yet lacks a physically interpretable scene representation and cannot learn from transient measurements as neural transient fields do. In this work, we attempt to address two key challenges for learning-based non-line of sight reconstruction. With only synthetic data available for training, we seek a carefully designed model that is robust to the approximations in light transport and hence can generalize well on real captures. Meanwhile, we hypothesize that a diverse set of supervision signals encourage the learning of holistic scene representations for better reconstruction. To this end, we seek a unified learning framework that supports diverse training objectives. The two challenges end up with the same solution, which is to combine physics priors with the power of deep learning. We now present our method. Our model embeds physics priors into a deep model to regularize its solution space. It includes three main components, namely an encoder that maps a transient measurement ht to a feature volume cs, a conditional radiance field that predicts the density and color at every 3D point given its feature vector, and a volume renderer that converts the radiance field into intensity images, depth maps, or transient histograms for training and inference given their respective forward rendering models. We now dive into each of the three components and highlight the key modeling decisions. Our encoder design is inspired by RSD, which transforms an impulse response of the scene into an intensity volume using diffractive wave propagation. Unlike RSD that operates on raw measurements, our encoder first learns to extract an XYT feature volume from the measurement and interprets it as featurized impulse response, which is subsequently transformed by RSD into an XYZ feature volume. Our encoder inherits the robustness of RSD and regularizes the learning of subsequent model components. Finally, our volume renderer queries the radiance field and synthesizes the desired target. One key strength of the physics-based volume rendering framework is its flexibility with respect to the forward rendering model. This allows our model to explore diverse training signals, including intensity images for supervised learning and transient histograms for unsupervised learning. For supervised learning and model inference, we adopt the same rendering integrals as NeRF for the synthesis of intensity and depth images. For unsupervised learning, we introduce a novel transient rendering formulation for the synthesis of transient histograms. The mathematical details are beyond the scope of this presentation. Please see our paper for more details. We now turn to the training of our method. Our learning objectives are a combination of reconstruction and regularization terms. Thanks to our flexible volume renderer, our model can learn to reconstruct intensity images using MSE loss or reconstruct transient histograms by maximizing the Poisson log likelihood. Additionally, we apply a beta prior on the cumulative transmittance to bias array towards either hitting or missing the object, and a total variation prior to eliminate spurious density of floaters in the reconstruction. At inference time, our model renders intensity and depth images of a scene in a single forward pass. The runtime of our method far exceeds the data acquisition rate of the hardware. The main bottleneck of our method lies in the volume renderer, which accounts for 80% of the runtime. We anticipate that our method will benefit from efficient rendering techniques in the NeRF literature. We now present our experiments. We first qualitatively compare our method with prior arts on synthetic data. All learning-based models are trained on a synthetic dataset of alphabets and digits and are evaluated on unseen objects from the same dataset or training objects with unseen poses. Our models produce sharper reconstructions and can sometimes recover invisible scene geometry indicated by the arrows thanks to the learned scene priors. Additionally, our method, despite not being trained on ground truth depth, can render plausible depth maps with the versatile volume renderer. Next, we report quantitative results using widely used metrics. On the alphabet dataset, our model trained with the two reconstruction terms combined consistently outperforms the baselines and other variants trained with a single reconstruction term. This highlights the strength of physics priors for learning-based reconstruction and validates our hypothesis that diverse training signals promote better reconstruction. To assess how the models generalize on out-of-distribution data, we challenge them on scenes with more complex geometry. As shown on the bottom, our models are worse than NETF++, a variant of NETF using our proposed transient rendering recipe. This is completely expected as the learned scene priors fall short in the presence of a domain shift and start hurting the performance. Nevertheless, the result shows the superiority of our transient rendering recipe, as NETF++ performs much better than NETF on complex objects. Most importantly, we compare our method with the baselines on real captures. As a reminder, real data look very different from synthetic renderings, and present significant challenges to learning-based methods that are typically sensitive to domain gaps if no special care is taken. As expected, LFE, NETF, and NETF++ all exhibit noticeable artifacts as they are not designed to guard against approximations in light transport. While RSD, despite being more robust, produces blurry images. In contrast, our models render crispy, artifact-free intensity images and recover plausible depth. This highlights the importance of the physics priors that prevent our method from overfitting the synthetic data. In summary, we present a DEEC model with strong physics priors for high-speed non-line-of-sight imaging. Our model consists of an encoder that embeds RSD for feature transformation, a conditional radiance field that learns scene priors from data, and a volume renderer that can flexibly render different targets for training and inference given appropriate forward rendering models. Our unified modeling framework enables learning from diverse supervision signals, supports fast feed-forward inference, and most importantly, generalizes well on real captures that approximate light transport in various ways. Thank you for listening.